First week of the cardiovascular unit by talking about return of blood flow. And this is something that last semester, and actually both semesters of last year, students struggled to understand. And so I want you to take the time to kind of go over this lecture, make sure that you pay attention in lecture to make sure that to help you understand this. And there's only two objectives here, okay? And we're going to talk about how we maintain blood flow, and get blood flow back to the heart, which is extremely important during exercise because we're actually pumping out a lot more blood than we are at rest. So when it comes to venous return, it's just the amount of blood that returns back to the heart. And this is affected by several things. So blood volume, your muscle pump, whether or not it's activated, the respiratory cycle, and the reason that that makes a difference is because that's related to the respiratory pump that we'll talk about, and the amount of resistance in the veins. So are they dilated, are they constricted, that sort of thing. Okay, but all of these variables affect whether or not we have venous, or how much venous return is occurring. So just to go through this really quick, sorry, I'm just getting a thing here. So blood volume, if I've got more blood volume, that will generally increase venous return. If I've got muscle pump activity, that will increase venous return. If I've got increased resistance, that's going to decrease it. And then the phase of the respiratory cycle, it depends. So if I'm inhaling, so I for inhale, that's going to generally make it easier to get blood in, but exhale, I'm going to have lower venous return. Okay, and we'll talk about that here at the end of towards the end of this lecture. Now, just from the fact that we're upright and we're tall, relatively tall, right? Like you think about your dog is upright, but it's still pretty low to the ground, whereas humans, not so much, right? And so there's some issues with that. And the big thing is gravity has a big effect. The taller you are, the greater the effect of gravity. Okay, and so what happens is blood pools or tends to just kind of hang out in the lower extremity or go preferentially to your legs. Okay, when we use the term pooling, that doesn't mean blood's just sitting there. We're just trying to give the idea that more blood volume will be in your lower extremity. And so the problem with this is that venous return is reduced. If I have less blood returning to my heart, then that means there's less blood that I can send other places like my brain. Okay, now this is exacerbated during exercise. Why? Well, cardiac output has to increase. We have to deliver more oxygen, and in order to deliver more oxygen, we need to have more delivery, greater cardiac output, right? We've talked about, or we've mentioned that cardiac output can increase by 5 or 6 times. Now, this is a good thing because it allows us to do stuff like run and play basketball and play football or whatever. But we need to be able to do that. And the way we do that is we have a greater heart rate and a greater stroke volume. Okay, these are all fine and dandy because they allow for this increased cardiac output, but it comes at a cost, or at least there's a difficulty, there's a problem with it, because if I have a greater heart rate, I've reduced filling time. So if I have a reduced filling time, that means there's less time for blood to get back into my heart before contraction. And so now we've got an issue. I've got less time to fill my heart up, but I actually need more blood anyway. So bear with me as we go through this. I've never tried this before, but I'm going to try this time. So we'll see if this works, and we might even do a demonstration in class. Okay, and I've changed some of the values a little bit just to make the math easier. So let's say that your normal cardiac output is 6 liters a minute. Your heart rate's 60 beats per minute. Your stroke volume is 100 mils. Okay, if your heart is beating 60 times a minute, that means there's every 1 second per contraction, or really this should say cardiac cycle. Okay, now remember that you're in systole or contraction for 1/3 of the time. You're in diastole for 2/3 of the time. So if we round that, that means you've got 7/10 of a second to fill your heart up with 100 milliliters of blood, and you've got 3/10 of a second to eject that much blood out of your heart. Okay, 100 mils is about a little more than 1/3 of a cup. If you have a standard 16-ounce water bottle, that's about 20% of that water bottle. Okay, but you've got to get that. That's not very much, but you've got to get that into your heart in 7/10 of a second, and then you need to get that much out of your heart in 3/10 of a second. Okay. So this gives you an idea of how hard your heart is pumping to get that much out, especially when you think about it. It's a tube going into a tube that's the size of your pinky. Okay? But now, let's change this up. Let's do max exercise. So we're going to say that you are a really elite athlete. Your cardiac output's 35 liters a minute. You're a young, healthy 20-year-old, so your max heart rate's 200 beats a minute. Your stroke volume's up to 175 mils. Okay? At 200 beats a minute, that means there's a 0.3 of a second per cardiac cycle. Remember, this isn't the best word. I should have said cardiac cycle. Okay? So cardiac, and this is horrific writing, but cardiac cycle. Okay? So that means you have 0.2 of a second to fill 175 mils of blood into your heart, and then you have 1/10 of a second to get that much out. 175 mils is about 3/4 of a cup, or about 3/8 of a water bottle, so a little over a third. So how are we able to do this? How are we able to get that much blood into our heart? Well, there's a couple of reasons, a couple of ways. And one we've already talked about. We mentioned torsion of the heart with the last set of lectures. Okay, just the fact that the heart's working hard, it creates a lot of energy, and it creates kind of this vacuum action that helps pull blood into the heart. Another way is the skeletal muscle pump. Okay, the design of humans, of animals, of whatever is ingenious. Okay, when we exercise, we need more blood. Well, the cool thing is, when we're exercising, we're using our muscles that need more blood. Just the action of the muscles helps get blood back to the heart. Okay, so muscle contraction increases pressure inside the veins. This is my go-gurt analogy. So we contract, that squeezes the veins, and that pushes blood up towards the heart. Okay, this increases venous return. When the muscles relax, blood falls back down towards my toes, but it doesn't go all the way back down to my toes because of these valves right here that are closed. Okay, so we squeeze it up, it falls back, we squeeze it up some more, it falls back, and we're able to help get blood back to the heart. Okay, another thing is the respiratory pump. Okay, the respiratory pump during inspiration helps get blood back to the heart. During expiration, it helps get blood out of the heart. Again, an ingenious design. When I exercise more, I need more oxygen in my body, so I breathe more. So by breathing more, when I take breaths in, I'm helping get blood to my heart. When I breathe out, I'm helping get blood out of my heart. So you got to remember that the diaphragm pushes down on the internal organs during inspiration. And so this creates a pressure gradient. So abdominal pressure is greater than thoracic pressure. And so this forces blood from the abdominal cavity up through the veins and into the heart. Okay? Remember, the heart's in the thoracic cavity. And so there's still blood leaving the heart, and there's still blood going to the abdominal cavity, that sort of thing. But we've created a situation where it is much easier to get blood back to the heart. I'm breathing more, my breaths are bigger, so I've got this massive gradient that I'm going to take advantage of, which will ultimately increase my venous return. Now but what's interesting as well is that this decreases stroke volume. What happens is my lungs expand, or our lungs expand, or are able to take in this extra blood flow. So blood, remember, goes into the right side of the heart. That's increasing venous return, the amount that's going into your heart. And then that blood goes into the lungs. In the lungs, we can open up more capillaries. There's greater pressure to get blood into those pulmonary capillaries. And it's a little difficult for it to get out of the lungs into the left side of the heart. And that sounds bad, but we don't just breathe in. We also breathe out. So our diaphragm relaxes, abdominal pressure is less than thoracic pressure, and so now we've got a pressure gradient that's going from the thoracic cavity to the abdominal cavity, and that squeezes blood out of the lungs, which also prevents venous return or decreases venous return. But as we're squeezing blood out of our lungs, we're increasing stroke volume, and blood is able to leave the body, or leave the heart, not the body, leave the heart and go to the rest of your body. Okay, so with the action of the muscle pump and with the respiratory pump and torsion of the heart, even though we've got decreased filling time, we can compensate for this by these pumps, by these ingenious designs. And that is where we'll end for the week.